Welcome. This question says 3 kilogram, 15 degrees C block of butter. So here's 3 kilograms, 15 degrees C butter. Is dropped into a calorimeter. There's my calorimeter that contains 10 kilogram, 40 degrees C oil. These are not really butter and oil. I'm making up numbers for them, but it's to give you a visualization. Show the equilibrium temperature. The result is 35.9 degrees C, and I give you sort of various parameters. We've got to visualize what we're doing, and if this is temperature and this is heat, then what happens is we basically warm up the cold butter. It starts off at 15 degrees C and its melting point is 20 degrees C. So that's the first job, that's the first term. And then we have to melt the butter. So there's my second term. And then once we melted the butter, any excess heat will be used to warm this to the T final, which is here. Now, all of this is paid for by the cooling of oil. So let's draw oil here. And the oil is already in liquid form, so it was solid and then it became melted, and now it's in the liquid form. And we're going to end up at the final temperature. We're going to get there by cooling down T hot. Well, I know T hot, don't I? This oil is at 40 degrees C, so that's 40 degrees C. And the heat that we give up in cooling down that oil is the heat that we're going to use to heat up and melt our butter. So it's like we had before for the ice melting to water. It's just that this time, because we have two different materials, we can't draw them on the same diagram. The heat lost by the oil is going to be the heat gained by the butter. And the final temperature is going to be the same for both of them. So does that help? Does that visualization help? It's not the best diagram in the world, but I think it shows kind of what's going on. I need some space. Let's try it. Let's just see if I can squeeze it in. I'm always a bit reluctant to do that, but let's just try. We'll put a line around here and we'll see if we can just squeeze this thing in. Okay, so 4 terms. So we have the mass of the butter times specific heat for solid butter times the temperature change for the butter, solid butter, added to the mass of the butter times the latent heat for butter, that's the second term, plus the mass of the butter times the specific heat for liquid butter, because now it's made liquid, times the temperature change for the liquid butter, plus the mass of the oil times specific heat for the oil times the temperature change for the oil equals 0. There's my 4 terms. Specific heat term, latent heat term, specific heat term, and a specific heat term. So let's put some numbers in. So looking at my text and also my diagram, 3 kilograms times the specific heat for solid butter And specific heat for solid butter is 2. It's not really 2, is it? But it's a convenient number. And then my temperature change. Well, my temperature change, it ends at 20, which is the melting point, but it starts off at 15. So this would be 20 minus 15. And then I have my mass of my butter, which is 3. And I have my latent heat for butter. I only gave you one latent heat here. It's the latent heat of crystallization, solidification, which is 6 joules per kilogram. And then this same material, so it's 3 kilograms still, but now I need, it's liquid, so I need the specific heat for liquid butter. And that would be 5. And then I have my temperature change for the liquid butter. If I look at my diagram, it ends at TF and it starts at 20. And then the final term, if I can squeeze it in, is the 10 kilograms of my oil times the specific heat for oil is 7 times the final temperature, which is TF, minus its initial temperature, which is 40 degrees, equals 0. Bit of a tight squeeze there, but we made it. So we have the heating of the solid butter, the melting of the solid butter, the heating of the liquid butter to its final temperature, and that is paid for by the cooling of the oil. And because I did T final minus T initial, the signs take care of themselves. T final is less than 40, so that's going to be a negative term. T final is more than 20, so that's going to be a positive term. So then I get, okay, this is 20 minus 15 is 5. 6 5s are 30, so there's my first term. Then for my second term, 6 3s are 18. And then for my third term, 15 TF minus 15 times 20 is 300. And then my fourth term, 70 TF minus, and this is 7 4s 28, 2,800 equals 0. There's my 4 terms. If I look, 2 of them contain TF, so let's drag those guys together. So I'm going to say, oh, okay, that's going to be 85 TF is equal to, well, this goes to the other side and is positive, so it's 2,800. And this 300 goes to the other side and is positive, which is 300. And then the 18 goes to the other side and is a negative, and the 30 goes to the other side and is a negative. So this means that 85 TF is equal to 3,100 minus 48, which equals 3,052. So TF is equal to 3,052 over 85, which equals 3052 divided by 85 equals 35.90, 35.9 degrees C. And that's what I'm supposed to find. So there we have it. The main difference between this, which is the oil and butter example, and the ice and water example, is that when I did ice and water, because melted ice becomes water then what you find is that the specific heat of this last term, which is the melted ice, which is now water, is the same numerical value as the specific heat of this term, which is hot water. So in that case, these two terms, these two numbers would be the same. But because I'm using different materials in this case, then these two are not the same numerical value because they're different substances. It's the same skill. It's just, pay attention to detail and visualize, and don't drop a term and don't assume TF. If you don't draw the diagram, it's easy to make a mistake about what is TF and what is, the melting point temperature. Just go step by step and work steadily through it. And there we have it.